In this presentation, we will explore how power is transmitted over long distances in the United States. We will also briefly explore how power is distributed within a house or in a clinical setting. In this presentation, I will refer to AC power and transformers. If you are unfamiliar with these topics, you might want to view the following presentations before viewing this one. To understand what alternating current is, it might be handy to understand the alternative, direct current. Alternating current is the standard for power transmission in the United States and is the power that is used in most modern X-ray machines. What alternates? And why does it alternate? Both questions are addressed in this presentation. Transformers play a pivotal role in modern power transmission. A basic understanding of their function will highlight their role in the story of power transmission. The War of Currents was not so much a war as a skirmish between George Westinghouse and Thomas Edison in the late 19th century. The short version of the story is that George Westinghouse and AC Power won the battle. It is much more economical to transmit power over long distances using AC power. To understand power transmission, you need to understand transformers. There are two basic types of transformers. The first is a step-up transformer. A step-up transformer will increase its input voltage to a higher voltage. If something increases, something else must decrease, and in the case of a step-up transformer, it is the amperage. So, if the voltage increases by a factor of 10 times, the amperage will decrease by a factor of 10 times. The step-down transformer works in an opposite fashion to the step-up transformer. It decreases the input voltage and increases the amperage by a proportional amount. For either of these transformers to work, they require AC power. When fed DC power, you will see a pulse of power when the power starts and another pulse of power when the power stops. For a transformer to work reliably, the power supply must constantly fluctuate, as in an AC waveform. Why are AC power and transformers the answer to power transmission problems? The answer becomes apparent when one considers the problem of transmitting power over long distances. We start with the power plant. One plant supplies power to a large number of households spread over a long distance. Siting power plants near households is not desirable. Power generation can be noisy, unsightly, and siting a power plant near residences is not a good idea. So we connect the plant's electrical lines to a power pole, and that pole connects to other poles at regular intervals. As many are needed to support the wire over a long distance. For simplicity, I'm omitting a number of intermediate technologies like substations and transmission towers that are actually used to support transmission. Let's say that we connect to a house that's 50 miles away. The problem stems from power loss in the long stretches of wire. Power loss is proportional to the resistance in the wire. And as the length of the wire increases, power loss increases in direct proportion, so that our 50-mile stretch of wire, the power loss is considerable. The most obvious method to address power loss is to reduce resistance in the wire. So how can we reduce resistance in the wire? Copper or aluminum are common conductors used for electrical distribution. Gold and silver are more conductive, but the cost of materials is prohibitive. Locate the power plant closer to the residences. This would mean that there would be more small power plants located close to the homes they serve. Power plants again are noisy, dirty, and siting power plants near homes is not a desirable option for the homeowner. Thicker wire inherently has less resistance. How about that? Thicker wire means that support structures like power poles would need to be larger to support the added weight. Additionally, thicker wire means the cost of wire would be higher, the conductor being a major contributor to cost. Supercool the wire like in an MRI scanner. Cooling wire to this degree would be expensive and impossible to implement. Liquid helium is used to cool an MRI scanner, and it must be maintained over the life of the scanner. The idea of cooling such a long stretch of wire is simply not practical. Did you notice that power loss is affected by two variables? The first being resistance, and the second being amperage. What if we were able to attack the problem from an amperage perspective? Let's suppose that our power plant wants to transmit 120 volts of power and 100 amps of current to your house. And they connect to a step-up transformer near the power plant that increases the voltage to 50,000 volts. In a step-up transformer, when the voltage is increased, the amperage is decreased by a proportional amount, so that if voltage increases to 50,000 volts, the amperage decreases proportionally to 22/100ths of an amp. On the power pole outside your house is a step-down transformer that reduces the voltage back down to 120 volts, and the amperage is restored to the 100 amps. Thereby, using transformers and AC current, we can economically transmit power over a long distance. The step-up transformer reduces the amperage by a whopping 450 times, and the power loss is reduced by the square of the amperage, which comes out to 202,500 times reduction of power loss over the long stretch of wire. The one disadvantage to this transmission scheme is the wire carries a high voltage. The high voltage requires a thick insulator on the wire and/or power poles that need to be tall and have heavy-duty insulators to isolate the wires and protect the public from electrocution. Just for information, we can estimate the voltage in a power line by the size of the tower carrying the lines. The taller the tower, the more voltage it will typically carry. A small tower or pole under 50 feet can carry from 12,000 to 35,000 volts. A tower from 50 to 100 feet typically carries lines that range from 33,000 to 138,000 volts. And a tower 100 feet or over can carry voltages from 230 to 500,000 volts. This large gray can mounted on the left side of the power pole is a step-down transformer. It is the one feeding my house. The lines on the top of the pole are distribution lines for the neighborhood, and they carry about 5,000 volts each. The green outlines the input wire and my house's step-down transformer. These wires coming out of the transformer leading to my house are outlined in blue, gray, and red highlights. This picture depicts the electrical connection and insulating anchor of my house. The diagram below is a clearer illustration of this connection. The top blue wire is hot and carries 120 volts at a phase angle of 0 degrees. Don't be worried about phase angle. It will be explained in the next slide. Gray neutral wire has no voltage and is a path back to the power company used to complete electrical circuits. The red wire is also hot and carries 120 volts generated 180 degrees out of phase with the blue wire. All three wires are gathered into a pipe and connected to the main house wires through the electrical meter. In my house, the electrical distribution panel is in the basement. These are the various plugs, light fixtures, and appliance circuits that are connected via circuit breakers or fuses. What does it mean that the red and blue wires are generated 180 degrees out of phase with one another? The blue wire's electricity is generated at a voltage of 120 volts at a phase angle of 0 degrees to the neutral wire. So any plug, fixture, or appliance that requires 120 volts is connected to the blue wire or the red wire and a neutral wire. Think of it as having a little man pushing electrons through the wire. Note that the power in the line constantly fluctuates from 0 volts to 120 volts in one direction, and then from 0 volts to 120 volts in the opposite direction. It is constant fluctuation of power that makes transformer perform its magic. The red wire is generated at a voltage of 120 volts at a phase angle of 180 degrees. Think of it as a small red man pulling the electrons through the wire. If the two wires, red and blue, are connected to an appliance, their combined electrical force is 240 volts. To supply 120 volts to a device, connect the red or blue wire to the device and use the neutral wire as the connection to complete the circuit. To achieve 240 volts, connect the red and blue wires to the device and their combined voltage add to provide a voltage of 240 volts. This depicts a standard outlet found in any American house, clinic, or hospital. Notice that the slot on the left is slightly larger than the slot on the right. The slot on the left is connected to the power company's neutral wire. The small slot can be connected to the power company's red 120 volt, 180 degree, or the blue 0 degree hot wire. Either wire can supply 120 volts of electricity to an electrical device, and the phasing makes no difference to the device being powered. The third hole is connected to a ground and is electrically connected to a large metal post driven into the ground of your house or clinic. It is connected to the frame of the device you're using to protect you from electrocution if a hot wire should come into contact with the case of the device in use. Most modern portable X-ray machines use batteries as their power source and use a 120 volt connection to recharge the batteries over a long period of time. This slide depicts a 240 volt outlet like a dryer, an oven, or an older X-ray machine might use. The top wire is the ground wire, and it is used to protect the operator if the case or housing of the machine should ever come in contact with a live wire. The slot on the left connects to one of the two hot wires. In this example, the blue 0 degree wire is connected to this terminal. The right slot is connected to the 180 degree red wire, completing the 240 volts necessary to power this particular device. Some 240 volt devices don't need a connection to the neutral wire. This is necessary if particular components inside the device require 120 volts to operate. The 240 volt wires and the plugs themselves are about 4 times heavier and not commonly used to power portable X-ray machines today. Some things to remember. The reason for using AC power in our modern world is that transformers work only with AC power. DC power will not work with a transformer. Trying to reduce power loss using a decrease in resistance is expensive and impractical. Decreasing the amperage before transmission is easily accomplished using a step-up transformer, and the power loss is reduced by the square of the amperage. As an historical note, portable X-ray machines used to be powered by 240 volt power. The machine itself was heavy and the power cords and plugs were also heavy and cumbersome. Hospitals needed to site special outlets outside patient rooms, one outlet serving multiple rooms. Modern X-ray machines use batteries to provide power, but you can bet that the DC is converted to AC before it reaches the X-ray production circuits. Stationary X-ray machines mostly use 240-volt power. It may be single-phase like is depicted in this presentation, or three-phase to provide more homogeneous X-ray beam. Thank you. This will end my presentation.